Hello everybody, welcome into another lesson. So today we are going to graph polynomial functions and we are going to analyze them, which analyzing will actually help us develop a graph for it. Now of course some of you are thinking, well, can't you use a graphing calculator? Of course you can, but you also have to know how to do it without using one. So what we're about to go over today is going to help us be able to do that. And one of the most important things actually came from yesterday's lesson when we talked about the end behavior of a polynomial function. So if we look here, we have f of x equals x to the fourth minus 2x to the third minus 3, right? Well, yeah, we have x with a couple different powers here and some constant, but what is the highest power? It's to the fourth power, meaning the degree of the polynomial is to the fourth power. So it's going to behave as a fourth degree polynomial, an even power polynomial. And furthermore, the coefficient on that x to the fourth term, the leading coefficient's positive. When you have a positive coefficient on an even-powered polynomial, what does that do for the end behavior? It rises to the left and it rises to the right, almost parabolic-like. Now, what this doesn't tell us is what the graph looks like in between the ends of the graph, what's going on in between. This is why you want to factor. Okay, so factoring, which I've already taken the liberty of doing, you'll get the quantity of x minus 1 raised to the third power times the quantity of x plus 1 to the first power. That tells you where your x-intercepts are. Those are absolutely critical for graphing. If you take x minus 1 to the third power set equal to 0, what do you get? You get x equals 1, so you'll get the point 1, 0. So let's plot 1, 0 because we're going to have the graph interacting with that point. If you set x plus 1 equals 0, what do you get? Negative 1. So you'll also have the point negative 1, 0. That's critical. So now we have plotted both x-intercepts. It's also a good idea to plot the y-intercept. So the y-intercept always occurs when x equals 0. So if you take 0 minus 1 to the third power times 0 plus 1, all that raised to the first power, you would just simply get negative 1 times 1, which would give you a y value of negative 1. So the y-intercept would occur at 0, negative 1. So let's go ahead and plot that too, the y-intercept, right? So we've now plotted both x-intercepts and the y-intercept. That's going to help us immensely here. All right. Now, that's great. We've plotted those. But there's some couple of other items we got to talk about to really get the shape of the graph. One of them is the power of the factors. You notice that x minus 1 is raised to the third power, and the x plus 1 is raised to the first power. So that x minus 1 actually accounts for 3 of your zeros, even though it looks like it's only one of them. It really accounts for 3 since it's raised to the third power. It's just repeated 3 times. Then you have x plus 1 is raised to the first power. That's another 0, so total you have 4 zeros. But if your factors are raised to an odd power, so let me write this down. If a factor is raised to an odd power, the graph crosses the x-axis at the particular intercept. So 1, 0 and negative 1, 0, both of the factors that produce those x-intercepts are both raised to odd powers. So the curve itself is going to fully cross through those points at the on the x-axis at those points. We'll get to even powers in a bit, but for now, remember, if it's odd, it crosses. Odd cross. That might be the best way to help you remember that. Odd cross. Okay? So we have that picture now, too, of what's about to go down. Then there's one more item we need to talk about before we attempt to graph this. And that's going to be what's called turning points. We got to talk about what are called turning points. So what are turning points exactly? Well, turning points are where the graph either goes from decreasing to increasing at a particular point, or vice versa, from increasing to decreasing at those particular points. Those are called turning points, where it turns from decreasing into increasing or increasing to decreasing. Either case, you have what's called a turning point. And whatever the degree of the polynomial is, you'll have one less than the degree for the number of turning points, at most. So if a polynomial, whoops, that's one word, not two, excuse me. If a polynomial is of degree n, the graph has at most n minus 1 turning points. There is a part 2 to this, but we'll get to that in a minute. So if a polynomial is of degree n, some arbitrary degree n, then the graph has at most n minus 1 turning points. Look at this particular polynomial. It's raised to the 4th power, right? It's of the 4th degree. That means that at most, 4 minus 1, it has at most 3 turning points. At most. Part 2 of this states that if all zeros of a polynomial function are real, then the graph has exactly n minus 1 turning points. Okay, so if all zeros of a polynomial function are real, then the graph has exactly n minus 1 turning points. So again, this is a 4th degree polynomial. Look at the factors. This is why we factor. So x minus 1, well, that's a real 0, right? So is x plus 1. Well, x minus 1 is 3 of your zeros, really. That's 3 of them, not just 1, because it's raised to the 3rd power. And then x plus 1's raised to the 1st power. So all 4 zeros of this function are real zeros. That means there's going to be exactly 3 turning points for this particular case. So now we know the end behavior, we know all the intercepts, we know the turning points, we know how many turning points it's going to have, I should say. Now at this point we're ready to graph it. So let's go ahead here and proceed to graphing. So end behavior, it rises to the left, rises to the right. That's going to help us. So from negative 1, 0, we go further left, it's just going to keep on increasing, right? The further left we go. and it's going to cross the x-axis at that point. Now let's draw to the y-axis here. So this is actually going to come down and around through the y-axis here at 0, -1. We're going to go up to almost 0, 1 until we can't reach it. Then it's going to be another turning point. Then we're going to cross. So there is what the graph of this roughly looks like. It may not be super exact because it's not a graphing calculator, but that's roughly what it's going to look like. You have 3 turning points. So if you start in the negative x's and keep increasing your number, your y value is actually decreasing until you reach this certain point, and then it starts increasing through the y-intercept. And then once you reach this point on the x-axis, it turns from increasing back to decreasing. Then when you reach this point, it goes back from decreasing to increasing. So we have the end behavior, the intercepts, and the turning points all accounted for. So this would actually be the graph of this function right here. You see 3 turning points. Now, once you've graphed, there's one more component to this. Yes, we have what's called an absolute max and min. So we have an absolute max and min. Now, absolute maximums and minimums, not absolute, excuse me, forgive me for that. That's going to be a local max and min. A local max and min. So, local means it's in the region. It doesn't mean it's going to be on the entire thing. There really is no local max because it keeps going to infinity in both directions, right? So we don't really have an absolute max, but we could have a local max. A local max you could think of as the top of a hill, right? You're on top of the hill. It's in that region, it's the highest point in that region. Think of it like a mountain peak. You could have mountain range rather. You have several mountains in a range. Well, you could be on the highest point on top of a particular mountain in that range, but it may not be the highest point in the entire range. Well, that would be considered a local max. A maximum is where it goes from increasing down to decreasing. How do you find that? Let's see. So to find the local max values, if they ever ask you to find the local max or min values, that's referring to the y-coordinate itself, the value of the whole function, the y-coordinate at that particular point. Without a graphing calculator, the best we can do is estimate, unfortunately. You can put it into a graphing calculator and then go to the extrema or the max-min feature on there and trace it and find those values that way in a graphing calculator around to so many decimal places, or you can graphically estimate it. It's not always exact. Here I'm going to say that's about, that would give you a y value of about -1/4. So y would equal -1/4. Alright, now the x values producing, what the heck's produling? Producing local max values. So if they just ask for the local max value, that refers to the y-coordinate. If they're asking for the x values producing the local max values, they're asking for the x-coordinate, which I'm going to say, looking at it, is roughly 3/5. Again, this may not be exact, but that's what it looks to be graphically. And it's an approximation. It's hard to do exact without a graphing calculator. Or if you go on to study calculus, there's something called the first derivative test, which will help with that. But that's a couple courses from now. Alright, so we found our local maxes. What about our local mins? Local mins you could think of at the bottom of a valley. If you look here, we have a local minimum. That's where it goes from decreasing to increasing, right? So again, the higher up I go in the x values, starting from the negative x's, it goes from decreasing till I reach this point, and then it starts increasing again. If it goes from decreasing to increasing, it's at the bottom of a valley, so that is a local min. We also have one right here, another local min. So the local min values, they're also asking for the y-coordinate in that particular case. So the y, I'm going to say, is about negative 1.25, which would be about negative 5/4. So y equals negative 5/4, as well as then let's look over at this minimum. I'd say about negative 3/4. Y equals negative 3/4 also. Then the x values producing the local min values, well, that's of course the x values that produce those local min values. So that would be, x would be about, I would say, negative 2/5 for the first one, and then your second one would be about 3/4, roughly. That's just a rough estimate. So that's how you find local max and min values. And I do got more here. We're going to do more. All right. Now that we got that out of the way, let's go on to the next one. Let's see. F of x equals x to the third minus 2x squared minus 11x plus 12. So we have f of x equals x to the third minus 2x squared minus 11x plus 12. Okay, so what's the degree of the polynomial? This time it's to the third power. What's the end behavior? Well, the coefficient, the leading coefficient's positive, and it's to an odd power, so that means it's going to fall to the left and rise to the right. We're going to treat this like a classic x to the third function, only now we know the end behavior, but we can't guarantee what it's going to look like in between the ends, okay? And first thing you probably want to do is factor, which again, I've already taken the liberty of doing that for you. So you would get x plus 3, that quantity, times x minus 1 times x minus 4. So this factors nicely into three linear factors. You have x plus 3 times x minus 1 times x minus 4. So let's start out finding our x-intercepts. Well, set each of the factors equal to 0, you would get negative 3, 0, which will put you right over here. Okay. And then, let's see. Actually, let's make one of these worth 2. There's a reason for that. Let's make one of these units worth 2 units. So negative 3, 0 will be right about there. Then x minus 1 equals 0. That would give you x equals 1. So here's about 1, 0 right there. And then x minus 4 equals 0. That would give you x equals 4. So 4 zeros the next one, right about there. So you have 3 x-intercepts. And of course, I'm going to highly advise we find the y-intercept. Just take 0, put it into each of your factors. So you would end up getting 3 times negative 1 times negative 4, which would end up giving you positive 12. So the y-intercept is going to be at the point 0, 12. So 2, 4, 6, 8, 10, 12. That would be right here. There's your y-intercept at 0, 12. So now we know all 3 x-intercepts and the y-intercept. All right. Now, let's talk about this here. Your not the end behavior, the intercept behavior. Each of these powers is only raised to the first power, right? Which means they're all 3 to odd powers, which means the curve will cross through the x-axis at those points. It'll actually cross through at those points. So, here's what that's going to look like then. Here's about what it's going to look like then. We also got to talk about turning points. The degree of the polynomial is 3, and all 3 zeros of the function are real. That means there's going to be exactly 2 turning points. There we will have exactly 2 turning points. So, we will go ahead now and proceed. So it falls to the left, right? We can proceed with that. Now let's go up from here roughly to the y-intercept. There's a turning point. There's 1, and dang it, these graphs, the way I put them together. There you go. So, you have 2 turning points. You've crossed through all your intercepts, and voila. There's roughly what the graph looks like, and it falls to the left and rises to the right. Okay? Now, with our 2 turning points, which means we have 1 local max and 1 local min. So, there's our local max right about here. So local max again pertains to the y value. That's going to be roughly about 13.5. So y would equal 27 halves. So what's the x value at that point? That's going to be about negative 1/2. So your local max would occur when the x has a value of negative 1/2. The y value, the local max itself, would be 27 halves. The max in this case, because the further right you go from the negative x's, it actually starts increasing till you reach that x point of negative 1/2. And then it starts decreasing again. Now, of course, we have a local min here, which would be like the bottom of the valley. So let's see, let's find the local min itself. The local min, roughly at negative 3.5, which would be y equals negative 7 halves, is roughly the local min. So what's the x value that produces that? That's going to be roughly 2.5, so that'd be 5 halves. An x value of 5 halves would produce that local min of negative 7 halves. So with all that, we've graphed and analyzed the curve. And then, let's see. I only have about 4 more. So I got about 4 more here. That can be a doozy. All right, what's the next one? Whoops, I don't want to do the factored yet. I want to write out the actual polynomial. All right, let's see. That's going to be x to the third plus 3x to the second minus 10x minus 24. Okay. So f of x equals x to the third plus 3x squared minus 10x minus 24, right? So what's the degree of the polynomial? It's to the third power, meaning it's an odd power. And the coefficient's a positive coefficient for the leading coefficient. So once again, the graph is going to fall to the left and rise to the right. What we don't know yet is the in-between behavior of this particular graph. This is where the factor comes into play. The factors, I should say. That's simply going to be the quantity of x plus 4 times the quantity of x plus 2 times the quantity of x minus 3. All right, those are your factors. So find each x-intercept. X plus 4 equals 0. That would give you x equals negative 4. We're going to make one of these actually equal to 4 units. One of these units would equal 4. So here's your negative 4, 0. There's a reason for that. You're going to see when we get to the y-intercept. X plus 2 equals 0, so x equals negative 2. That's going to go about right there. And then x minus 3 equals 0. That would give you x equals positive 3, which would go right about there. Another important thing to understand then are the powers. The factors are all 3 raised to an odd power. So that means the curve will cross the x-axis at those points. So that we know that now. And let's see. We should also find the y-intercept, which would be simply 4 times 2 times negative 3, which would give you 8 times negative 3. That would give you negative 24. So the y-intercept is going to occur at 0, negative 24. So let's see, 4, 8, 12, 16, 20, 24. So there's 0, negative 24 right there. There's your y-intercept. All right. Now we got to discuss turning points. How many turning points? Well, all 3 zeros of this cubic function are real zeros. So you'll have exactly 2 turning points. So now we know the intercepts, we know the turning points, we know the end behavior. Let's graph this. So this is going to fall to the left because it's an odd power with a positive coefficient, and it crosses each of the intercepts, so it's going to come about there. And ladies and gentlemen, that's about what your graph is going to look like. So, it falls to the left, rises to the right, as we would expect. And we've gone through all the intercepts and all that. So, now that we've done so, we have 2 turning points, which means, look at this here, we have a local max and a local min. About this point here, we have a local max, so let's find out. Let's find out what that local max is at the top of that hill. Local max is the y value, so that's going to put you at about 3. So y would equal 3 So what would the x value on that be? That'd be at about negative 2.5, right? So negative 5 halves. So when x is about negative 5 halves, you have a local max at y equals 3. Then let's find the local min, which is a little bit past the y-intercept. So the local min is going to put you still at negative 1. No, it's right on the y-intercept. It's just the way it's drawn. The local min itself is that y equals negative 1. The x value that produces it is 0. So in this case, your y-intercept actually happened to be the local min. So the turning points indicate where local maxes and mins are. And I got about 3 more. All right. Let's see what we have here. This is a little bit different. Flip those notes. We have a 4th power one. F of x equals x to the 4th plus 12x to the 3rd plus 52x squared plus 96x plus 64. That one looks like a doozy, doesn't it? So f of x equals x to the 4th plus 12x to the 3rd plus 52x squared plus 96x plus 64. Well, let's establish the end behavior first. The degree of the polynomials to the 4th, right? It's an even power polynomial and the coefficient's positive, so that means it's going to rise to the left, rise to the right. So we've established the end behavior. Now, why don't we write out the factors of this? The factors are simply going to be, it's actually pretty easy, the quantity of x plus 2, that quantity squared, times the quantity of x plus 4, that quantity squared. So we have x plus 2, that quantity squared, times x plus 4, that quantity squared. Well, here's the thing. I think, so for every x value, every x unit will still count as 1. But for every y value, let's count that as 8. There's a reason why I'm doing this, because when we get to the y-intercept, that's going to help us. But if you set x plus 2 to the 2nd power equal to 0, you get x equals negative 2. So you'll have an x-intercept at negative 2. And then x plus 4 raised to the 2nd power will give you x equals negative 4. So you'd also have negative 4, 0. Right? Okay. Also now, let's talk about the y-intercept. Well, you would end up just getting 2 to the 2nd times 4 to the 2nd, which would end up equaling 4 times 16, which would equal 64. So your y-intercept is actually all the way at 0.64. That's why I said we'll count every x unit here as 1 for 1 value, but every y for 8. So that's going to put you all the way up here at 0.64 for the y-intercept. That'll help get you a better graph. All right, so now we also got to talk about the intercept behavior for these x-intercepts. All right, notice both of these zeros are raised to even powers. This is where it changes. if a factor of a polynomial function is raised to an even power, then the graph touches but does not cross the x-axis at that particular intercept. Okay. So if a factor of a polynomial function is raised to an even power, such as these two here, the graph touches but does not cross the x-axis at that particular intercept. So we'll see how that looks in a minute, but the best way you can remember this now, because when we talked about when it was an odd power, it does cross. But if it's even, it only touches. So how you can remember that is if you even touch. If you even touch. That's the best way you can remember that. Alright? And then of course we got to talk about the number of turning points there are in order to get the full picture. Well, notice something. It looks like only 2 zeros, but each factor is raised to the second power, meaning each of these is actually 2 of the zeros. So you have a total of 4 zeros because it's the 4th degree, and all 4 zeros are real numbers. They're real. So since you have 4 real zeros, that means that you're going to have exactly 3 turning points in this case. So now, let's start with our furthest away, our furthest left x-intercept. So it rises to the left, doesn't it? So it's going to look something like this, rising to the left. Now, here's where it's important. You're going to only touch the x-axis here and not cross. So that means it's actually going to go back up around again until you reach about here. You're going to come back down and touch the next x-intercept since it's raised to the second power also. And then you'll come back up again since it only touches, and we'll just proceed through the y-intercept, which would be right about there. So there's roughly what the graph of this function is going to look like. It looks like a weird W almost, doesn't it? Kind of cool. So you have actually 3 turning points. So let's go ahead now and take our local maxes and mins. We have about only one max. So the local max is going to be right about here, which would put you at about -3 1/4, so that'd be about -13/4. So, well, actually, I'm thinking of the x. Excuse me. The local max itself's the y. That would be about 8. That'd be about 10. No, that'd be about 12. So local max is y equals 12, since we did 8 units, and then, yeah, the x value that produces that would be about -13/4. Now, we have 2 local mins, but the good news is, whenever you have even power intercepts, those usually act as your local mins, or maxes, depending upon which way it's tilted. But the mins are going to be easy. Local mins because we have two values of 0, right? Y equals 0. Those are your minimums because it only touches the x-axis but doesn't cross. The x values produced in them are going to be -4 and -2. Those are your local mins. So there's that function. I have about two more. All right, let's see, what do we have here? Two more, all right, so we have f of x equals x to the third minus 6x squared plus 11x minus 6. So f of x equals x to the third minus 6x squared plus 11x minus 6. So what's the degree of the polynomial? It's a third degree, right? What's the coefficient on that? What's the leading coefficient? It's a positive. So that means it's going to fall to the left, rise to the right. Now what we don't know is the in-between behavior, but we'll figure that out. Again, that's where the factoring comes in. So your factors of that are going to be the quantity of x minus 1 times the quantity of x minus 2 times the quantity of x minus 3. So we have three linear factors. Quantity of x minus 1 times the quantity of x minus 2 times the quantity of x minus 3. So let's go ahead here and find our x-intercepts. That'll be, of course, 1, 0, 2, 0, and 3, 0, right? Okay. And, of course, it's going to be useful to find the y-intercept. So you'll end up getting, let's see, -1 times -2 times -3, which should give you -6. So the y-intercept itself will occur at 0, -6. 4, 5, 6. That'll be right down here is your y-intercept at 0, -6. All right. So we found all our intercepts. Let's establish the x-intercept behavior. Each of these factors is raised to the first power, right? To an odd power. So that means the curve will fully cross the x-axis at those points. And last but not least, let's talk about the turning points. The degree of the polynomials to the third, and all three zeros are real zeros. That means there will be exactly two turning points. So now we can proceed to draw this. The end behavior falls to the left, rises to the right. So let's come down here till we go through the intercept, the y-intercept. So there's the falling to the left, and it crosses at each of the intercepts. So come to about here, and then turn through to cross, then come to about here, turn through to cross, and look at that. It rises to the right and falls to the left, and it crosses through all three x-intercepts. Look at that, how nice that is. And we have two turning points. We have where it goes from increasing to decreasing, and then from decreasing to increasing. So those are our two turning points. So we have one local max and one local min. So let's go ahead and find the local max first, up on top of that hill. What is the local max? It's a little south of 1, so I'm going to say about 9/10. Y would equal about 9/10. What x value produces that? That looks about half to me, so x would be at about 1/2. Now, what's a local min? The local min looks to have if you look at the graph, has a y value of about -1. So y would equal about -1. Your x value would be about, I'd say about 3/4. So x would equal, actually that'd be 2 3/4. So that would be 11/4 would be that. Would produce that local min of -1. So there's the graph with your local maxes and mins. And I have one more, just one more. All right, last one, everybody, then we're done. So let's see, this is a good one. F of x equals x to the 4th plus 3x to the 3rd minus 9x squared minus 23x minus 12. Okay. So f of x equals x to the 4th plus 3x to the 3rd minus 9x squared minus 23x minus 12. Start with the degree of the polynomial. What's the degree? It's to the 4th power. Okay. Now what's the leading coefficient? It's positive, isn't it? That means then it's going to behave as a 4th degree polynomial, an even power one, so it's going to rise to the left and rise to the right. Now that's part of the story. We need to know what it looks like in between. So let's take the factors here. What are the factors of this polynomial? That's going to be a really fun one here. We get the quantity of x plus 4 times the quantity, let me write this on a different line because I'm going to run out of room. So x plus 4 times the quantity of x minus 3 times the quantity of x plus 1 raised to the 2nd power. So this is different. You're going to see just how different this is here in a second. So the factorization is the quantity of x plus 4 to the 1st power times the quantity of x minus 3 to the 1st power times the quantity of x plus 1 to the 2nd power. Well, let's find our intercepts here, okay? You have, of course, -4, 0. 2, 3, 4. Here's your -4, 0. You have, let's see, you have positive 3, 0 right there. Then you would have -1, 0 right here. So every x unit will count as 1, but I think we need to make every y unit count as 2. You're going to see why. Let's find the y-intercept. So that would give you 4 times -3 times 1 to the 2nd power, which would end up just giving you -12. So your y-intercept will be at -12, 0, -12. 2, 4, 6, 8, 10, 12. So 0, -12 is right there. All right, so there's our y-intercept. Now, we know it's ultimately going to rise to the left and rise to the right. We also need to know the turning points. Well, first let's talk about the intercept behavior. You notice that x equals -4 and x equals +3, those two factors are raised to an odd power, which means the curve will cross the x-axis at those points. However, look at x plus 1, that's raised to the 2nd power, an even power. Remember, if you even touch. So that means that x equals -1, the graph will touch the x-axis there but not cross. So we have both types of behavior occurring with this graph. So we know that, and then we need to find the number of turning points. Well, the degrees to the 4th all 4 zeros are real, so that means there are exactly 3 turning points. Now we proceed to graph. So it rises to the left, so we'll start there, right? It's also going to rise to the right. Now at -1, it's going to touch there. So let's go down and then go back up till we about touch it. So there's that part. Then this is going to loop around again. And that's a weird graph, but we have, well, that's too many turning points. I didn't draw that right. Hold on a minute here, guys. There we go. There's that graph. I know that looks really weird, doesn't it? Looks really weird, but you'll have that. So as you see, it rises to the left, rises to the right. It crosses through x equals -4 and x equals +3. It only touches at x equals -1. And you have 3 turning points, which is what you should have. So that tells you the whole story of how to draw the graph. Now, last but not least, we're going to have one local max, which happens to be at x equals -1. So your local max, the y value for that would, of course, be 0. The x value would be, the x that generates that would be -1. Now we're going to have to deal with 2 local mins. We have 2 local mins there, which you'll find right here and right there. Now we're just going to have to graphically estimate them. So let's see, the y values went by 2, so 2, that's 4, so about 3. So a 3.5. So y would be equal to -3.5, that's -7/2. You also have another y minimum value. Let's see, at 2, 4, 6, 8, 10, 12, 14. So also -14 is another local min. And actually it's the absolute min if we're being honest, because that's the lowest point you see on the graph. Now the x values that would produce those results, let's go to y equals -7/2, so to about -2.5, so that'd be -5/2. And then what produced the -14, that would be about +1/2. So those are your local max and local minimum values. And again, graphically, those are estimates. If you put this into a graphing calculator and use the trace with either the extrema or the max or min features, depending upon how your calculator words it, you can get decimal answers, approximations. And then when we take calculus and we learn about the first derivative test, you can actually get exact methods, but not till then. But this has been it for the polynomial functions unit. The next lesson we start the powers, roots, and radicals unit. The very next lesson will actually be about nth roots and rational exponents. So I hope everyone has a great day. Take care.